All right, guys, Assalamu alaikum. Today we are doing IGCSE Chemistry P6, October number 2024, variant 1, paper 6. All right, so let's look at the first question. A student has a mixture of copper 2 carbonate powder and crystals of sodium sulfate. Copper 2 carbonate is insoluble in water. Sodium sulfate is soluble in water. The student tries to obtain pure copper 2 carbonate and crystals of pure sodium sulfate from the mixture. Figure 1.1 shows four of the steps the student carries out. All right, so the student is trying to remove two solids from one another on the basis of solvent. All right, meaning using a solvent to separate them. Like for example, in water he will add water, so sodium sulfate will dissolve, but so copper carbonate would not, and then copper carbonate he would collect it as a precipitate, and then he would just have the precipitate of copper 2 carbonate, collect that, and then the filtrate, that would be solution of sodium sulfate, and then he would heat that to collect sodium sulfate. Well, let's look at the question. State what happens to sodium sulfate in step 1. In step 1, when he adds the mixture in water, sodium sulfate would dissolve, so we will say it will dissolve. All right, it will dissolve. Next question. State what is removed from filtrate in step 3. In step 3, what is being removed from filtrate? The water is being removed, right? So when we are heating it, we're evaporating water. So we're going to say water is being removed from step 3. Describe what must be done after the filtrate has been heated in step 3 to obtain a larger amount of sodium sulfate crystals. We are attempting the method. By the sentence, we can know which method we are attempting. Heat the filtrate from step 2 until crystals start to form. All right, until crystals start to form. After that, what do we do to obtain more crystals? We let it cool down. All right, so we'll say let the solution cool down. After, let the solution cool down after heating is stopped. So what will we observe? We will observe that more precipitate will form. Full stop. Next question. State what must be done to the residue before it is allowed to dry in step 4 to obtain pure copper 2 carbonate. What must be done in step 2 for this residue before drying it? We should rinse it with water, right? We should rinse it with water. Rinse it with water. Why do we want to rinse it with water? Because the copper 2 carbonate is going to be soaked, right? It's going to be wet. Why is it going to be wet? It's going to be wet because it was part of this solution that had sodium sulfate in it. Now, once you filter it, some water might be stuck between the copper 2 carbonate. That water might contain uh, the sodium sulfate dissolved in it, right? Ions of sodium and sulfate. They would act as impurities. So what do we want to do? We want to thoroughly wash this, rinse it completely so that all the sodium sulfate that is stuck beneath them gets washed away. All right. So you wash insoluble residue always before drying it. All right. Rinse it with water. Identify the substance removed from copper 2 carbonate in D part 1. D part 1. Where is D part 1? Acha, this one. When we rinse it with water, what are we removing? We are removing left over, or basically stuck. We can use the word stuck. Not stuck, trapped. Trapped trace quantity of sodium sulfate, because it would be stuck with water, right? On to the next question then. Question number 5. A student investigates the reaction between aqueous magnesium sulfate and aqueous barium nitrate. All right, so they're seeing the reaction between magnesium sulfate and barium nitrate. You would know what happens because it contains the sulfate and it contains the nitrate. They are both going to join and white precipitate is going to form. Well, a huge experiment is written. The experiment is done like 8 different times. So what we need to do is we need to measure a lot of things we need to measure a lot of things. That's what we need to do. So let's just measure a lot of things, use the information. So volume of aqueous magnesium sulfate, volume of aqueous barium nitrate. All right. So how do we know what is the volume? So we're probably going to add probably going to have to see from over here what the experiment was and everything. So in experiment one, they added 4 centimeter cube of magnesium sulfate and 1 centimeter cube of aqueous barium nitrate, right? Now in experiment two, they repeated experiment one, but instead of using 1 centimeter cube of barium nitrate, they use 1.5 centimeter cube of barium nitrate. And in and magnesium sulfate, they just use the same amount, right? Magnesium sulfate use the same amount. So let's look. Magnesium sulfate, they still use the same amount, 4.0, but over here they use 1.5. All right, they use 1.5. Okay. Now in experiment two, in experiment three, they use 2.5 centimeter cube of barium nitrate instead of one. In experiment 4, they use 3 centimeter cube of barium nitrate. In 5, they use 3.5 centimeter cube of barium nitrate. In experiment 6, they use 4.5 centimeter cube of barium nitrate. In experiment 7, they used 5.0 centimeter cube of barium nitrate. And in experiment 8, they use 5.5 centimeter. So they never change the volume of magnesium, which is 4.0, right? So what we need to do is, all we need to do is write 4.0 every single time. So let's just keep duplicating it. Let's just keep duplicating it. All these will be 4.0. All right, there will be no other value other than 4.0, because every time only 4.0 centimeter cube of magnesium nitrate is being added, but barium nitrate is changing. Like one time it is 1.5, then it is 2.5, then 3.0. So after that it is 2.5, then it is 3.0. After 3.0 it is 3.5, and then 4.5. All right, 3.5, and then it is 4.5, and then it is 5.0, and then 5.5, 5.0, and 5.5. All right, now we have to tell the levels. So the first one, the level was 1.2 because it was at 1.2, right? Now the level is 1.6, 1.7, sorry, 1.5, 1.6, 1.7, and this should be 1.8, right? So this value will be 1.8. Now this value is going to be exactly 3.0. The reason why I wrote 3.0 is because everything is written to one decimal place. So we have to continue to write to one decimal place. All right. Then it is at 3.1, 3.2, 3.3, 3.2, 4, 3.5, 3.6. All right. So after that, it is at 3.6. Then it is at 4, 4.1, 4.2. So it is at 4.2. And then it is at 4.5, 4.6. This is 4.6. 4.6. This is 4.2. Okay. This is 3.6 and this is 3.0. All right. So this is 4.6 now. All right. And I suppose now the level is going to remain 4.6, even if you add more and more barium nitrate, 4.6 and 4.6, meaning
Does
no
this
more.
mean magnesium sulfate is the limiting one now?
Magnesium sulfate is the limiting one now, and barium is now starting to become in excess. All right. So after 4.5, we are seeing that barium is now starting to become excess. Next question we want to add on a graph, first of all. Okay. So now you can see at the bottom, they've mentioned the axis and they've labeled it. Over here, they want to tell us about the level of precipitate on the measuring cylinder. On the measuring cylinder, the maximum value is 4.6, meaning we can take 5 as a whole number as the cap, and we can go from 0 to 5, right, on the graph. So let's go 0. So let's make it 1.0. Let's make it 2.0. Let's make it 3.0. And let's make it 4.0. And let's make it 5.0. All right. And then they're probably going to ask us to plot stuff. So at the bottom, volume of aqueous barium nitrate, when 1.0 barium nitrate was added, 1.2 centimeter cube of precipitate was formed. So this is 1.2, as you can see. This would be 1.2 precipitate, and this is volume of barium nitrate. So the precipitate that formed was this much, right? After that, at 1.5 centimeter cube of barium nitrate, the level of precipitate was 1.8. So let's write that down. At 1.5, this is 1.5 centimeter cube of barium nitrate, beta, and the level is 1.8. This is 1.8, as you can see. All right. And then at 2.5 centimeter cube of aqueous barium nitrate, 3.0 centimeter cube of barium precipitate is produced. At 2.5 beta, the value of precipitate is 3.0. After that, at 3.0 volume of barium nitrate, 3.6 centimeter cube is produced. So let's make that one. 3.6 centimeters produced, that is right there. All right, and then after 3.0 there is 3.5, and at that 4.2 centimeter cube is produced. This is 3.5. All right, that was 3.6. Now 4.2 is this one. All right, at 3.5 we are going to see 4.2 centimeter cube of precipitate being forming. All right, and then after that 4.2 at 4.5, 5.0, and 5.5, 4.6 centimeter cube is producing. Is there 4.0? There's no 4.5, 5.0, and 5.5. 4.5, 5.0, and 5.5. On all three of them, 4.6 centimeter cube is being produced. So at 4.5, at 5.0, at 5.5. All right, 4.5, 5.0, and 5.5. Now they have asked us to draw two straight lines of best fit through your point. The first straight line should be for the first 5 experiments and must extend pass through 0, 0. Okay, so it should start from 0, 0 and it should go through the first 5 points. So that's 1 point, 2 point, 3 point, 4 point, and 5 points. So all 5 points are in a straight line. That is actually very pretty. All right, so we've drawn the straight line, and the second straight line is going to be through the 3 points. So the second straight line is through the 3 points. They are basically going to tell us that this graph is going to help us identify the volume of barium sulfate, which was actually required, and what is the volume of barium sulfate after which everything is in excess. All right, so that is basically it. Next question, use figure 2.1 to reduce the level of precipitate on the meshing cylinder when the experiment is repeated using 2.8 centimeter cube of aqueous barium nitrate. So we want to check at 2.8 centimeter cube. So for that, I'll just change the color. 2.8 is right here. All right, so we want to measure the level of precipitate at 2.8. So all we have to do is go up. All right, once we go up, then we are going to go this way. All right, and going this way, we can see that it is very close to 3.1, 3.2, 3.3, 3 point, yeah, so it's between 3.4 and 3.3, but it is very close to 3.4. So we can call it 3.38, right? 3.38. I'd like to call it 3.38. You can call it 3.4 as well. 3.38 centimeter cube, right? Because it is not exactly on 3.4, it is between 3.3 and 3.4. But because it is between 3.3 and 3.4, that is why writing 3.38 would be good. Okay. Next, just highlight it as well. Next, the student repeats the experiment using 6.5 centimeter cube of aqueous barium nitrate. Predict the level of precipitate on the measuring cylinder. Explain your answer. So even if he uses 100 centimeter cube of barium nitrate, it's not going to produce a level greater than 4.6, right? So the level of barium precipitate would be 4.6 centimeter cube. And why would it be 4.6 centimeter cube? The answer is very simple. The answer is because any any barium nitrate added will have no magnesium sulfate to react with, because all the magnesium sulfate would have already reacted. All right. So we will say that all magnesium sulfate would have run out
सर कैन यू
after
रिपीट, मुझे समझ नहीं आया.
reacting with approximately, beta, I will repeat once again. How much, at what volume do we think that all the magnesium sulfate would run out? At roughly 3.5, 3.6, 3.7, 3.8, at roughly 3.85 centimeter cube of barium nitrate. So approximately 3.85 centimeter cube of barium nitrate, BaNO3 whole twice. है ना बेटा? you're asking, आपको समझ नहीं आया? The question is saying कि look, in the experiment, the maximum volume of barium nitrate they used is 5.5. They are saying what would be the level of precipitate if they use 6.5 centimeter cube of barium nitrate? The answer is the level would still be 4.6. Why would the level still be 4.6? Because there is only a certain amount of magnesium sulfate, right? Is keep using more and more other reactant, but if the original reactant is running out at 5.5, it's definitely not going to produce more product if you use 6.5 centimeter cube of barium nitrate. It's like saying okay, I have poured one glass of milk and one glass of water in a teapot or in a boiling kettle, and I have put 7 tea bags. All right, and I am expecting to make 100 cups of tea, but you can't put 100 tea bags, but because you've put only 1 cup of water and 1 cup of milk, you're probably going to make a maximum of 2 cups of tea, right? You have to have both reactants increasing proportionally, or if you do not have both reactants increasing proportionally, then one of the reactants is going to act as limiting, and it is going to determine how much of the product is formed, right? So regardless of
Yeah.
you using 6.5 centimeter cube of barium nitrate, the level of
Hmm.
precipitate would form would be based on the magnesium sulfate, because as Mariam had said previously, magnesium sulfate is going to become the limiting one and going to determine how much of the product is forming, right? So that is why even if
Yeah.
you use 6.5 centimeter cube, 4.6 centimeter cube of product is formed. And that is what we've written, that magnesium sulfate is the one that is running out. So it doesn't matter how much barium nitrate you use. All right.
All right.
Next,
जी.
sketch on figure 2.1. The graph obtained if all the experiments are repeated using aqueous barium nitrate of half the concentration used in experiment 1.128. All right. So if we use half the concentration of barium nitrate, then that means that half the moles of barium nitrate are present in every volume. Does that actually make sense? Let's suppose everything had a concentration of 1 mole per dm cube. All right, or let's even make it even easier for us. For now, let's take the concentration as 1 mole per centimeter cube. That means in 1 centimeter cube of this solution, there is 1 mole of barium nitrate. There is 1 mole of barium nitrate. In 1.5 mole centimeter cube of this solution, there is 1.5 moles of barium nitrate, right? Now they are saying decrease the concentration by half. So that means now the concentration make it 0.5 mole per centimeter cube. Now it means that in 1 mole of this solution, there is 0.5, in 1 centimeter cube of this solution, there is 0.5 mole of barium nitrate, right? So if the moles of reactant decrease, the product decreases to half. So that means in the first reaction, the product will be 0.6. In the second reaction, the product will be 0.9. In the third reaction, the product will be 1.5, right? In the fourth reaction, the product will be 1.8. Where is 1.8? That is when the when this when our barium nitrate is of half concentration. All right, that is what they have asked us to sketch. Okay, so we are going to have just a few lines, of half the gradient. Let's suppose the first line should go through 0.6 at 1. The second line, instead of going through 1.8, should go at 0.9, like this. And the third line at 2.5 was going at 3.0, should go at 1.5 now. And after drawing three lines, you should know that it should go in a straight line, right? So it will go in a straight line all the way actually. Why it will go all the way? Because the maximum level of precipitate that can form is 4.6. That means if you're using this concentration, all these volumes of barium nitrate will now react. All the volumes of barium nitrate will now react because they have not yet reached 4.6. They'll keep reacting. At one point, this concentration and at some point, the volume will actually become in excess. Like, for example, I'll give you an example when it would become in excess. If this concentration of barium nitrate was becoming excess at 3.85, then if you decrease the concentration to half, then about 3.85 times 2, which is 7.6, 7.7, about 7.7 centimeter cube of barium nitrate would be required to completely react with the 4 centimeter cube magnesium sulfate now. All right, I hope that makes sense. Okay, so this is our line. That is going to be of half the concentration. Next, suggest why the measuring cylinder is inverted several times after the aqueous barium nitrate is added. Why is the thing inverted several times? We're trying to mix it up, right? We're trying to mix it up so that the precipitate are completely settled as well. All right. So we want to settle the precipitates so that we can measure their level. Any precipitates that are stuck on the sides up above the all the precipitates that are formed, they will actually fall down and they will actually be collected at the bottom. All right. And all the liquid will be removed from between the precipitates as well. So all those things that they can be answered. All right. So it is inverted for many different reasons so that
To mix the reactants.
all, yeah, we can also say okay, we are actually mixing the reactants. All precipitates. A very good word is agglomerate. All right. Agglomerate means clump up at the bottom. Agglomerate at base of cylinder, base of M EASURING, measuring cylinder. Full stop. Also for mixing. So it is also inverted for mixing. It is also inverted several times for mixing. For mixing.
The first part of your answer actually answers the next question.
Does it? Let's see. Suggest why the measuring cylinder is left to stand before the level of precipitate is recorded. Yeah, so that everything completely
yeah.
settles, all the precipitates, so that all the precipitates settle at the bottom. So that all the precipitates,
Can I use the word agglomerate here?
yeah, precipitates agglomerate and settle at the bottom. So if I'm using agglomerate over here, I wouldn't use it up above because that's not the style we like to go with, right? So that all precipitates agglomerate at the bottom. Don't use the same thing twice. Agglomerate at the bottom of the measuring cylinder. Bottom of the measuring cylinder. All right. So we can might as well just erase this. We can say it is inverted several times for mixing the reactants. All right. Next question. The volumes of both aqueous solutions are measured using burettes. Give a reason why burettes are used rather than measuring cylinders. Why do we use burette rather than measuring cylinder? Because burettes have a higher degree of accuracy, right? So we will say burette have a higher degree of accuracy. Burettes have a higher degree of accuracy. Suggest why burettes are used rather than volumetric pipettes. So why do we not use pipettes and why are we using burettes? Why are we using
Because
burettes?
because
Why are we
the
not using pipettes?
volume,
I
we don't
haven't
know the
read the
volume.
experiment. Because
Yeah,
we don't know the
because
We don't
volume.
know the
pipettes
volume
only have a fixed volume, so and we
Because
don't know the volume, so
we don't know the
because
value, yeah.
but we nahi, the thing is better we do know the values over here. You can't say because we don't know the value. We are the one who are choosing how much barium nitrate we are adding. So we do know the values
so
every
it's like
time in
different
every
values,
reaction.
so that's
But
why.
yeah, the values are different and pipettes usually they measure a certain amount of values. So right. So because the values are variable, right? Or the because values are not fixed. Because values of barium nitrate, because values of barium nitrate in each experiment are not fixed. All right, the values they are not fixed. Okay, on to the next question. This question is completed. It was out of 40 marks. This question alone was 19 marks, so that was 50% of the paper. Let's go to the next question. A student tests two solid T and U. Solid T is lithium sulfite. All right, so it is uh, Li2SO3. You should know that, right? Sulfite is SO3, lithium is Li. Complete the expected observation. The student carries flame test on solid T because it contains lithium ions. Because it contains lithium ions, it should have the color
Red.
very good. It should
Red.
have the color red. If you don't remember that, it is written right here. Okay, it is written right here. If you don't remember, but if you do remember, then just write red. All right. Right over. Next question. The student dissolves the remaining solid T in water to form solution T. Student divides solution T into two portions. Student adds the first portion of solution T to a test tube containing acidified aqueous potassium magnate 7. Alright, state the color change. Okay. So he's adding potassium magnate. Why is he adding potassium magnate? Because there is SO3 sulfite ion present. And if you go to your tests for anions and if you look for
Purple to
tests for
Purple
colorless.
less to
SO3 minus,
color. Yeah.
yeah, purple less to
What?
color, nahi, purple to colorless.
Purple to
Yeah.
colorless.
GG, purple to colorless. If you have sulfide ions, right, you can oxidize them to SO4 minus 2 ions, sulfate ions by adding potassium magnate. The color will just change to purple. The color will just change to colorless from purple. Okay. So we are going to say color changes from purple
From purpleless to color.
to colorless.
Guys, I'm tired.
Right. Okay. To the second portion of solution T, the student adds excess dilute nitric acid. The gas produced turns filter paper soaked in acidified aqueous potassium magnate 7 white. Oh, okay. Identify the gas produced of T. The student adds excess dilute nitric acid. Okay, because he
That's
added
with
dilute
the
nitric acid
sulfate.
and the gas produced and the gas turned the sulfur the gas turned potassium magnate white, meaning the
Oh,
gas which
sulfur
decolorizes
dioxide.
potassium magnate. Yeah,
Sulfur
there is
Not
also
dioxide.
sulfate.
another test for gas
Sulfate.
right here. No, sulfur dioxide, beta. Look, sulfur dioxide because the gas is going to do it. Now you're not going to look for the ion. Sulfate is an ion. You're going to go in the gases section and you're going to see who turns acidified potassium magnate colorless. Sulfur dioxide does. All
Sulfur
right. So
dioxide.
they're asking us to identify the gas, right? So we are going to say identify the gas produced sulfur dioxide. Okay. Next question. The solution produced in C part 1 Student adds aqueous barium nitrate. In C part 1, because he added dilute nitric acid and sulfur dioxide gas was produced, that means definitely the sulfite is finished now. There is going to be lithium nitrate,
White
right?
precipitate.
There is going to be lithium nitrate over here. Okay. If we add barium nitrate to lithium nitrate, white precipitate will actually not form.
Ammonia?
Nothing will happen,
Okay.
right? Why should something happen? There is the same ion, so there will be no reaction.
Wait, can you please explain?
Look, because it's said to the portion of T. You know T is what? Lithium sulfate, right? So lithium sulfate LiSO3, Li2SO3 reacted with nitric acid HNO3 and it produced sulfur dioxide for a start, right?
Mhm.
So it should also have produced lithium nitrate, right?
Yeah.
Okay.
And it should also have produced water
Water?
because
Yeah.
you are going to balance the equation and the equation is going to fit perfectly like this, right? You put 2 here and 2 here, right? This should be your equation. Now, water is water, sulfur dioxide is the gas that left you, and lithium nitrate is the salt that is present, right? Now, in a solution of lithium nitrate, you're adding barium nitrate. Barium nitrate does anything when there is sulfate present. Is there sulfate present over here?
No.
In the product, is there any sulfate present? No. So will there
No.
be a white
No.
precipitate form? No. But you
No.
should
Oh.
understand that not every test result is a positive result, right? Sometimes there are negative results. Negative results say no change, right? Because barium nitrate is not a reagent for testing this. It doesn't test anything in this, right? Next question then.
Right.
Test on solid U. Solid U contains one cation, one anion. Okay, he added a few drops of aqueous ammonia and a green precipitate was formed. If a green precipitate was formed when aqueous ammonia was added, then that means that it's either one of two things. It's either Fe2 plus ion or it's either chromium
Chromium.
3 plus ion, right? Because those are the only ions that produce green color, right? No one else produces your green color. Next, to the second portion, okay, to the second portion of solution U, add 1 centimeter cube of dilute nitric acid, followed by few drops of silver nitrate, and a yellow precipitate is formed. That means iodide ions are present,
Wait,
right? Because
wait, it's either chromium or for the one
Fe2
before that?
plus. Yeah, it is either chromium or either Fe2 plus.
Oh, okay, okay, okay.
Why is it either chromium or either Fe2 plus? Because beta,
Because
if
in
you
the
go
back.
downstairs, yeah, if you go
Yeah.
here and you look at the cations and you look at effect of ammonia, you're going to see for chromium that green precipitates are formed. You're going to see for iron that green precipitates are formed. Only chromium and iron have green precipitates when they are added to ammonia. All right.
I remember this because yeah, the sir said justifies the colors. Don't
Yeah,
revise
there are
anything
only
else.
4. Yeah, if you want to
Yeah.
remember the cations for that was for P4. For this, you don't even have to remember anything, right? You can just check.
Yeah.
But for P4, I had explained to you guys, beta, dekho, there is going to be something that is going to come, right? So all you have to do is remember the colors of 4 transition elements. There are 8 cations that you have to remember. Out of them, one cation doesn't even give a color. It produces ammonia gas, that is ammonium ion, completely different. Aluminum, zinc, and calcium, they give white precipitate. Chromium and iron, iron 3 plus, it gives green precipitate. Fe3 plus, iron 3 plus gives red brown, and Cu2 plus gives blue. All 8 are done. That is how you remember them. Now, what happens in excess is a difficult story to remember, but for P6, you don't have to do that either. You can just go check at the bottom. All right, next question. For before question, let's read test 3. The third portion of solution, you add 1 centimeter cube of aqueous chlorine. The solution turns brown. Solution turns brown because a displacement reaction would have taken place because chlorine is more reactive than iodide ion. All right, identify 2 cations that test the observation shown in 2.3.1. Show could be in solid U. I don't know how I
Wait,
read
can you
that
explain
sentence,
the
but
last one again?
I will explain to you one more time. Look, because there is an iodide present. First, let's take, for example, if sample contains iron ions, right? So U is actually FeI2 then, right?
Okay.
If it was.
Okay.
And we add chlorine. Because chlorine is more reactive, we've studied that more reactive halogen displaces a lesser reactive halogen, right?
Mm.
So what would happen over here? FeCl2 would be produced and
FeCl2.
iodine aqueous would be produced. This iodine aqueous would be the brown solution.
Okay. Okay. Okay.
That
But
is
how
what
do
is
you know
happening.
it's iron and not chromium?
No, he said
I said
hypothetically, like,
suppose, hypothetically speaking, if it is iron. I did not uh, confirm, right? So let's do it in an ionic way so that I don't have to hypotheticalize myself. Plus Cl2 gives 2Cl minus plus I2, and this is brown. This is the displacement reaction that has taken place, all right?
okay.
Next, identify two cations. So the two cations are Fe plus 2 or Cr plus 3. These are the two cations that must be present, right? We've already discussed. Next question is describe an additional test that the student could do to confirm which one of the two cations identified in T is in solid U. Give the expected result for one of the cations. So what could we do? Instead of just adding a small portion of ammonia, if we add it in excess in chromium, it will remain insoluble. Fe2 plus, it will also remain insoluble, but the PPT will turn brown near the surface, right? Right. But even better, what could we do? We could add aqueous sodium hydroxide to another portion and chromium would dissolve, but Fe2 plus would not, right? So we will say add aqueous sodium hydroxide drop by drop until in excess. Add AQUEOUS aqueous sodium hydroxide drop by drop until in excess. All right.
Can we
If
also like say how we can just use ammonia, because then it's soluble and insoluble, right?
ammonia, both of them are insoluble. That is what I
Oh, okay,
just
okay.
observed. In
Okay,
ammonia,
okay.
we see that even Cr3 plus is insoluble, and we see that Fe2 plus is insoluble. Yeah, we could determine that Fe2 plus would start to become brown because of oxidation if it is left to stand. But why not just add sodium hydroxide to another sample of U and get the result manually by ourselves? Why wait, right? We're going to say add aqueous sodium hydroxide, sorry, sodium hydroxide, aqueous NaOH because there's not much space. NaOH, sodium hydroxide, drop by drop until in excess. If the cation is Cr plus 3, then green precipitate will form, which dissolves in water, which dissolves in excess, which dissolves in EXCESS. All right. Identify the anion in solid U. The anion is your iodide ion. Iodide ion, right? I minus for stop. Next question. Beetroot is a colored vegetable. The color is caused by a mixture of water-soluble colored compounds. Plan an experiment. This is chromatography. To find out how many water-soluble colored compounds there are in beetroot. Include in your how to extract colored compounds from a beetroot. All right, beta. So for that, you're gonna first take a mortar and pestle and beat the beetroot till its roots are separated from its beet. I'm joking. What you have to do is just absolutely crush it, though. You wanna make a juice of it, and then you're going to filter it, right? Remove all the basically you're gonna add some water in the crushing thingy, the mortar and pestle actually, all right, and then you're going to filter it. The soluble component you're going to do chromatography of it by taking a drop of it and putting it on the chromatography paper. Khali wali, you're gonna observe how many spots are produced,
Are
and that many components are there, right?
are juicers part of common laboratory apparatus?
Beta, juicer, I mean, uh,
How
they
are we
are
gonna crush it?
they are not the blender and the juicer are actually supposed to be part of it. I mean, at larger levels in labs वगैरह they are, but for you guys should know what mortar and pestle is. So that is why always whenever you're trying to crush stuff, you say mortar and pestle, all right? Don't say juicer and blender.
Okay.
There are many
The
reasons why.
mortar is the peesne wala, right?
The mortar is the, yeah,
Thak.
the peesne wala, and pestle is basically the plate
Thing
or
you
the
piece it
pyala.
with.
नहीं
Oh,
नहीं,
acha.
the bowl.
Yeah.
The
Oh,
bowl
okay,
is,
okay.
I think, the
Yeah.
pestle, and mortar is the dum. All right. Uh,
Okay.
in Urdu we call it silbatta, and
Mhm.
I did not know
20
that.
years 20
Yeah, same.
years from today, I mean, in the past, when there was no Shan biryani masala and no national kadai masala, people used to make their own spices at home. So these experiments basically were part of household matlab practices. Like our grandmother, she used to crush all the spices herself at home, and then she used to store them after drying them in the sun. For one day after drying them in the sun, she used to store them in like flasks and vessels. So these were part of household practices, the mortar and pestle and everything. Now, of course, uh, आप लोग तो माशाल्लाह से बर्गर और पिज्जा और मतलब I mean छोड़ देते हैं. Acha, I forgot we are on recording, so let's continue studying. Beetroot is a colored vegetable. The color is caused by a mixture of water-soluble colored compounds. Plan an experiment to find out how many water-soluble. Yeah, so we know. So we are going to say that take a beetroot, take a beetroot, and do you know in mortar and pestle you shouldn't put it directly. You should first cut the beetroot in very thin slices, right? Cut it in cubes or something. Take a beetroot and cut it into small pieces. Why do we cut it into small pieces? So that we don't have
So
to
that's
crush it
easier.
much. Yeah, so it is easier
Yeah.
to crush into small pieces.
So are we gonna do another paper after this?
And then
Yeah.
can we have this one finished first? And then um, add it or crush it using mortar and pestle. Pestle, pestle. Full stop. Add water to the mortar and pestle. Pestle, so that our colored substances dissolve in it thoroughly. Full stop. ठीक है? Now filter the mixture to remove all insoluble components. Components. Full stop. Now take 1 drop of filtrate and carefully place it on the pencil line drawn
So don't we place it like above the pencil line?
No, we place it exactly on the pencil line, but the pencil line must be above the solvent. That is
Oh,
what we
okay.
have to mention over here as well. All right. So carefully place it on the pencil line on the chromatography paper. On the chromatography paper. Full stop.
I feel like this is the easiest. Paper
Now,
6, last question.
Yeah.
this is such a generic question. Like this comes so many times. Now dip the chromatography paper in a beaker containing water in such a way that only that the pencil line, the spot and pencil line are above water slash solvent. Basically, why I have said that the beaker should contain water is because they've told us that the components are water soluble. So I know which solvent we are using. But if you do not know which solvent you are using, so over here you are putting chromatography in a beaker containing not water but a suitable solvent. The word used over here instead of water would become a suitable solvent. All right. In such a
Okay.
way
And How
that
do
the
we
spot or how do we what?
how do we know that it's not water?
No, it is water, but if we don't know, then
Right
use
now,
suitable
for
solvent.
this question, we know that the mixture dissolves in water. But if they had not
Oh Lord.
specified, if it they had not specified which solvent it dissolves in, then we just said
Yeah,
in a suitable solvent. Okay.
yeah, Jay.
All right. Next question is no next question, next line that we should see is observe the spot separating into different components as it travels up the chromatograph. So chromatograph is basically the paper. All right. So after we have seen the number of the spots have completely separated, once no more spots are separating, count the number of spots. These are the number of substances. All right. So once no more spots are
Sir, could
separating,
you scroll up just like by one line a little bit?
once no more spots
Yeah,
are,
thank you.
no problem, beta. Once no more spots are separating, just what do we do if no more spots are separating? What do we do? We basically count the number of spots, right? Count the number of spots or colors separated. Stop. And in the question, they had asked the main goal. The main goal was you wanted to check out how many water soluble colored compounds there were. So yeah, so these are the number of water soluble colored compounds present in beetroot. Full stop. And with that, this past paper has been completed. Any questions?
No, sir.
Wait, so is it like bottom, bottom of the line or above the line?
What is bottom of the line or above the line?
The solvent is
The
bottom of the
water.
line.
The
Okay.
solvent is below the line, not even bottom. Below.
Okay.
Have I written bottom?
I don't know.
The
I don't think so.
solvent. Look, if this is your chromatography paper, beta, and this is your pencil line and this is your stop, the solvent should be here. Should be
Okay.
below the pencil line. Always below the spot. And if someone asks you why the solvent is always kept below the spot, because the solvent will cause this guy to dissolve in it if it comes in contact directly. Do you understand?
Okay. Makes sense.
You don't want that happening. Okay.
Mm-hmm.
All right. So this paper has been completed.